This is Alan here to talk about linear systems, and this video is specifically about the topic of resonance. Let's start with the idea of power factor and resonant frequency. In a resonant circuit, the input voltage and the current are perfectly in phase, so the phase angle is 0. This corresponds to a power factor of 1. Before we go any further, let's take a look at what I'm talking about when I say that the phase angle between the input voltage and the current is 0. So let's go to our whiteboard for just a moment. It's important to note here that we're talking about AC power, because in a DC circuit, the voltage and the current are always in phase. So in the AC circuit, let's say that this blue is our voltage, and let's say that this red is our current, and we'll go, how do I want to do this? I'm going to go here actually, and these are exactly 180 degrees out of phase. So that's like saying that this red one had to get bumped this way 180 degrees to then be in phase with the blue one. If you did shift that red one to the right that far, it would be perfectly in phase with the blue one, and they would be perfectly in sync with each other. And then that would be a resonant circuit. So currently it's not a resonant circuit. And we can make it a resonant circuit by changing the frequency of the signal. And yeah, so that's what I'm talking about when we say that they're in phase or out of phase. So let's go back now to our slides. Still on that first slide. When the voltage and the current are in phase, when they're perfectly in phase, we say that we have a power factor of 1. The power factor of a circuit is equal to the cosine of the phase angle, and it represents the efficiency with which generated power reaches a load. So you want a power factor of 1. It means the power you're producing is actually getting to the load with very good efficiency. In order to create a resonant circuit, the inductive reactance, we'll talk about these more in a second, and the capacitive reactance of the circuit must offset each other. Because inductive reactance X sub L equals omega L, and capacitive reactance X sub C equals 1 over omega C, a resonant circuit exists when omega L equals 1 over omega C. All that is we're saying that XL has to equal XC in a resonant circuit. The frequency of the AC voltage can be adjusted to make this happen. So we're talking about the frequency in your sinusoidal voltage. The frequency that balances the capacitive and inductive reactances is the resonant frequency. When we say it balances, that's what we're talking about. That resonant frequency, the capacitive reactance and the inductive reactance are going to balance each other out. Basically, they're going to cancel each other. And whichever frequency accomplishes that is the resonant frequency. All right, if we don't have a resonant circuit, if resonance has not been achieved, then it could either be a capacitive circuit or it could be an inductive circuit. So let's talk about the capacitive circuit first. We say that a circuit is capacitive when the capacitive reactance exceeds the inductive reactance. This means that the phase angle between the input voltage and the current is non-zero. In this situation, the current leads the voltage, and so the circuit is said to be leading and resonance is not achieved. The power factor of the circuit is equal to the cosine of the phase angle between the input current and the input voltage. What does that all mean? Let's go back to our whiteboard for just a minute. Check this out. This is, well, I shouldn't do that. It's not good. Alright, let's say, let me remember how we want to draw this. Let's go there, and we'll go there. And this is, let's say this is our this is our reactive power, and this axis represents our real power. Alright, that reactive power is our X. Remember we had XL and we had XC? Alright, so your omega L will be, anything with omega L will be shown, let me get a different color. Omega L will take us this way, and omega C, or 1 over omega C, will take us this way. Now, actually 1 over the omega C is J times 1 over omega C, like J being kind of like I, like it's going to be on the imaginary axis, and really that's the same as negative J omega C. So I can scratch this right here, and this is just negative J omega C. The negative tells you that it's downward on this imaginary axis. So if it's inductive, then you're up here. If it's capacitive, then you're down here, and you need them to balance out. And we say that in a capacitive circuit, we're going to be further here, we're going to be stronger in this direction than we are in the inductive direction. And our power triangle, it's going to be reflected by this. And then you're going to have this phase angle right here. And we say now that the current, I'm sorry, I actually drew that backwards. Back up for just a second. I'm sorry guys, I've got these going the wrong way. So let's clean this up. Your J omega C is up here, and your negative J omega L is down here. So if we've got a capacitive circuit, then we're actually going to be in this region. Our phase angle is going to be here. And here, this is our current leading. It's leading because the phase angle is positive, right? Think of it as counterclockwise, being leading. And our voltage is here on the x-axis. So our current is leading our voltage, and we say that this is a leading circuit for that reason. Let's go back now to our slides and talk about the inductive circuit. Right, and this is just the opposite of what we talked about before. So a circuit is inductive when the inductive reactance exceeds the capacitive reactance. This means that the phase angle between the input voltage and current is still non-zero, but it's in the other direction. And we say that the current lags the voltage, and so the circuit is said to be lagging, and resonance is not achieved. Right, notice that in both cases, the terms leading and lagging are used according to what the current is doing relative to the voltage, not the other way around. The power factor of the circuit is equal to the cosine of the phase angle between the input current and the input voltage. And that's something, the power factor, that I did not address that on the last time we went to our whiteboard. So if we could, let's go back to our whiteboard. And I don't want you to be confused. This is on the whiteboard. This is the capacitive power triangle. And so I didn't change it for the inductive that we just talked about. But power factor is calculated by taking the magnitude of this. We'll call it S. Right? Take that magnitude of that, we're talking about this right here, all right, which is notice you've got a right triangle here. So if you know your real power and you know your reactive power, you can find the magnitude of this vector here. All right, that multiplied by the cosine of this phase angle here gives you your real power. All right, and the power factor is simply that cosine theta. All right, so all right, let's do this. I just said basically that magnitude of that vector times cosine theta equals the real power. So that means that cosine theta equals the real power divided by the apparent power. And that's usually, we want it to be 1, all right? But it's not going to be there, but you can usually achieve, and like Georgia Power, it requires it to be so for big manufacturers and certain facilities, especially big facilities that are using up a lot of juice. They require it to be somewhere in the neighborhood of like 0.9 or 0.95. It's usually going to be about 0.9 or 0.95. It's really high, and if they're not getting that, then the engineers at that particular facility they could get a bank of capacitors, and they basically have to adjust their power triangle, but they use real machines to do it, and that's a little over my head how they rectify it so far. But I hope this helps a little bit. Let's go back to our slides now. We just talked about power factor. Let's talk about quality factor. Quality factor refers to the ratio of the reactive energy stored in an inductor to the resistive energy dissipated. And the quality factor also indicates the shape of the resonance curve, which displays the total impedance of a circuit over a range of frequencies. So when we say it displays the total impedance of a circuit over the range of frequencies, that means that your y-axis is going to show that impedance, Z, and your x-axis is going to be the frequencies, F. Notice this case that the frequencies it's F, it's not omega. And if you have to do a conversion, just remember that omega equals 2 pi F. So F equals omega over 2 pi. For a low Q, low quality factor, the curve is short and relatively flat. And for a high Q, the curve is narrow and has a very pronounced peak. Quality factor refers to the ratio of the reactive energy stored in an inductor to the resistive energy dissipated, as we just said. And here we've got two equations, one for a series RLC circuit. You can calculate the power factor as it shows there. And the other shown here is for a parallel RLC circuit. And yeah, so I hope this helps, guys. Good luck in your preparation for the FE. And that's all for today. Bye-bye.